Welcome to the Explainer. We all know you can't predict an earthquake, but what if you could prepare for every possible earthquake? So today, we're going to dive into the incredible science that models thousands of potential futures, all to help protect us from one of nature's most powerful forces. Just take a look at this. Spread across North America is this incredibly complex web of seismic activity. Every single one of those dots is an earthquake, a little reminder that the ground we stand on is in constant motion. This is the reality of the risk we face, from California's famous San Andreas Fault to the lesser-known but still powerful zones right in the middle of the U.S. and down into Mexico. And that, right there, is the fundamental challenge, isn't it? For the engineers who build our cities, for the insurers who protect our homes, and really, for every single one of us. You just can't know when the next big one will hit. So, what do you do? Okay, let's get into it. To start, we've got to accept a hard truth. We are dealing with a force that is almost random and has just colossal power. Look, seismologists can't send us a calendar invite for the next major event, so they've taught us to ask better questions. The whole focus has shifted from trying to predict the unpredictable to really understanding the potential consequences. And for that, well, we have a deep and often pretty destructive history to learn from. Just think about that number for a second. 9.2 on the moment magnitude scale. That scale measures the total energy an earthquake releases, and a 9.2 is, well, it's a monster. That was the power of the 1964 Good Friday earthquake in Prince William Sound, Alaska, the biggest ever recorded in U.S. history, a true titan. So let's see how this violent past gives us the critical data we need to model what the future might actually hold. This timeline really shows that seismic risk is a coast-to-coast story. You have the 1700 megathrust quake off the Pacific Northwest, so powerful it sent a tsunami all the way to Japan. Then, in 1812, an earthquake in Missouri literally rang church bells in Boston. And in 1985, an offshore quake absolutely devastated Mexico City, hundreds of kilometers away from the epicenter. The takeaway? No region is truly immune. And when you look at the sheer scale of the largest U.S. events, you see a really clear pattern. Alaska, sitting right on top of a massive subduction zone where one tectonic plate is diving under another, just completely dominates the list. The energies we're talking about here are just staggering. And this quote right here, it illustrates a crucial point. The damage isn't just about the raw power of the quake. It is so much about the ground beneath your feet. See, Mexico City is built on an old, soft lake bed. So when the seismic waves from that 1985 quake hit that soft soil, it was like hitting a bowl of jello. They were amplified enormously, turning what was distant shaking into a complete catastrophe. Okay, so you have all this chaotic history, all this complex geology. How on earth do you turn that into a practical tool that you can actually use to prepare for the future? This is the game changer. Modern risk analysis doesn't even try to predict the one next earthquake. Instead, it uses immense computing power to simulate tens of thousands of possible earthquakes. It's like creating a complete virtual inventory of everything that could happen. The whole process is broken down into 4 key steps, and each one builds on the last. So first, the model generates this massive catalog of potential earthquakes, all the what-ifs. Then, for every single one of those, it calculates how intense the ground shaking would be at every location. After that, it figures out how different buildings would respond to that shaking. And finally, it puts a dollar figure on all that damage. But hold on. Before any of that can happen, the model has to know exactly where everything is. That's geocoding. It's the process of assigning a precise latitude and longitude to every single building, from a skyscraper in San Francisco to a family home in Missouri. It's the absolute foundation. Without this step, the rest is just guesswork. Okay, let's look at the real heart of the model, the engine that actually imagines all of these possible futures. Now, that word stochastic might sound complex, but all it really means is that the model includes a huge range of possibilities, and each one has a calculated probability. It simulates everything, from the small, frequent tremors to those incredibly rare but devastating megaquakes that might only happen once every few centuries. And this, right here, is the crucial point. It's this fundamental shift in thinking. Old-school prediction was completely obsessed with answering when. Modern catastrophe modeling asks a much more useful question. What if? What if a magnitude 7 hits this fault? What if a 9 hits that subduction zone? It's not about trying to nail one outcome, it's about understanding the entire spectrum of risk. So, how do you analyze all of this with pinpoint precision without, completely melting a supercomputer? Well, the model uses a very clever mapping technique. It's called a variable resolution grid. And you can see exactly how it works on this slide. The model lays a grid over the map, but the grid isn't uniform, see? Over the ocean or rural areas, the squares are really big. But then look at downtown San Francisco. The grid becomes incredibly fine, down to 100-meter cells. It focuses its analytical power exactly where the people in the property actually are. It's just brilliant. Okay, so the model simulates a quake, and it knows how hard the ground is going to shake at every single point on the map. The next big question is, so what breaks? And this is where the vulnerability module comes in. You can think of it like a digital crash test, but for buildings. It knows that a modern steel frame skyscraper is going to behave very differently than, say, an old unreinforced brick warehouse. It takes into account the construction type, the year it was built, its height, all of it, to calculate a specific damage estimate for each building, in each and every earthquake scenario. The model also has to be smart enough to account for different types of seismic threats, because not all shaking is the same. The sharp, violent shaking from a strike-slip fault like the San Andreas in California feels very different from the deep, rolling motion you'd get from a massive subduction zone event like the ones off the coast of Mexico or in the Pacific Northwest, and the model understands and simulates both. So at the end of all this incredible computation, what do you get? You get something profoundly useful. This is not just some academic exercise, it's actionable intelligence. Insurance companies use it to make sure they can actually pay all the claims after a disaster. Engineers use it to design safer buildings, and city planners use it to write smarter building codes. This is literally how we build a more resilient society. This technology moves earthquake risk from this abstract, terrifying force of nature into a variable, something we can measure, manage, and actually plan for. It forces us to confront this powerful question. Now that we can see the risk in such high definition, are we really making the smartest choices about where and how we build our world?